Hello, welcome back. We've been talking about water and the way that we mix most things into water. And when we mix things into water, we create what we call aqueous systems. So we want to talk more about these aqueous systems today. And then I'm going to come back to the energy, to the heats of vaporization, to those Q equals MC delta T stuff from the last lecture. But first, water is an aqueous system. An aqueous solution is simply a water sample containing some dissolved substances, usually ionic, doesn't have to be, it could also be molecular, like sugar dissolves in water. In a solution, the solvent is what you are dissolving in, like water, and the solute is what is dissolved, the dissolved particles, like salt. Solvents and solutes can be liquids, gases, or solids. Here, like if water is the solvent, it's a liquid. The solutes, like salt, may have started out as a solid. And even though it is in an aqueous solution, once it's done, it still is, if I take away the water, it would be solid again. Okay. Solutions are generally homogeneous mixtures. What that means is that I can't filter it out. If I take salt and put it in water, the only way to get the salt back is to boil the water away. I have to take the water away. I can't filter it to get the salt back out. And that salt is evenly distributed, so that if I took a container of salt water and poured half of it out, each of the containers of salt water now would be the same. Each one would have the same salt concentration. Okay, so that's a solution. So I can take it and I can take a little bit out, and I know that what I took out was the same as what's left. So I can make solutions that way. Now the process of making a solution is called solvation. Not salvation, solvation. The process of dissolving a solute. So there's some terminology. Now, ionic and polar covalent compounds dissolve really well in water. Okay, why? Because like dissolves like, I already told you. And with ionic compounds, what actually happens is that the ions break apart. So sodium chloride doesn't stay sodium chloride. When you add it to water, the water at the surface interacts with the sodium and the chloride ions through hydrogen bonding, and it pulls atom by atom, cation by cation, anion by anion, ion by ion, it pulls the ionic compound apart through these physical polar interactions. So it dissolves it. So it's still sodium chloride, but now it's sodium ion and chloride ion that are in the water, and that makes them available for chemical reactions. Now, because of this, polar solvents dissolve polar and ionic compounds, nonpolar dissolves nonpolar. We call that like dissolves like, because you need those interactions, and nonpolar compounds interact with nonpolar compounds, and polar and ionic compounds interact with polar and ionic compounds. Now, if it turns out that when you dissolve something, it conducts electricity, that is a special term called an electrolyte. All ionic compounds and a few polar are electrolytes, meaning they will conduct electricity. If you are a weak electrolyte, what that means is that you did not dissolve entirely. If you are a non-electrolyte, it means that you don't conduct electricity at all. A weak electrolyte conducts electricity a little well, but it didn't dissolve completely. Like part of the solid is still in solution. It's not a great conductor of electricity. Some polar compounds are non-electrolytes in pure state, but become electrolytes. So if I take ammonia, which is a liquid, ammonia does not conduct electricity. If I add ammonia to water, it becomes an electrolyte, although weak, it's a weak electrolyte, but it's still an electrolyte because some of that ammonia, NH3, will become ammonium, NH4 positive. So the nonpolar ammonia becomes an ion which can now conduct electricity. And so basically, if you have a polarity or a charge, you conduct electricity. And you are either a strong or a weak electrolyte. And whether you are a strong or a weak electrolyte just depends upon how well you dissolve. Hydration, and we talked about this before in a lab with copper 2 copper copper 2 sulfate pentahydrate, where we figured out what the water of hydration was. Water of hydration just means many crystals, in order to become stable, will absorb a little bit of water. They pull the water right out of the air, and once it's in there, they form what's called a hydrate. And a common example is copper 2 sulfate pentahydrate. This process of gaining water is called desiccation. If I have a compound that has water that loses the water, we call that efflorescence. So a hydrate is something with water. If it loses that water, it's called efflorescence. The way I remember that is I know the word effervescent means like bubbly, and this is, so it's giving something off. So efflorescent is giving off, but in this case, water. If you are hygroscopic, hygroscopic means that you take water out of the air. So if I take copper 2 sulfate and I burn that water off, and the water is now gone, it now will reabsorb that water. So copper 2 sulfate is hygroscopic until it has 5 waters of hydration, and then it no longer takes water out of the air. Calcium chloride is a really good desiccant. Another really good hygroscopic desiccant, a hygroscopic compound is sodium hydroxide. If you are so hygroscopic that you turn yourself into a solution, so like copper 2 sulfate, calcium chloride, they absorb water out of the atmosphere, but only so much, and then they stop. Some compounds will keep absorbing water. An example being sodium hydroxide. If you leave sodium hydroxide out, it will eventually just turn into a sludge because it will keep taking water out. It will until it forms a solution, a very concentrated solution that you would not want to touch, but it works that way. So let's talk a little bit more about water of hydration. And in fact, maybe we didn't do this lab yet. I thought we did. Maybe it comes with this chapter. But how do we calculate the percent mass in water, of something in water? It's just, if I want to know how much water something has, I just take the mass of the water divided by the total mass times 100%. So let's say I want to know what the percent mass of sodium carbonate is. If it's sodium carbonate decahydrate. Well, the mass of 10 waters is 2 times 1 is hydrogen times 10, and 16 is oxygen times 10. Add that all together, I get 180 grams per mole. If I take the sodium carbonate, if I take 2 sodiums, sodium is 22, 23, I can't remember the exact number. It might be one of those that's like 22.5. I think it's 22.09. I can't remember exactly. Carbon is 12. Oxygen is 15.998. But I take the sodium times 2, the carbon times 1, the oxygen times 3, add them together, I get 106 grams. We've done that many times. So if I wanted to know what the percent mass of water was in sodium carbonate decahydrate, I would do 180 divided by the total, which is 276. So that's really the only math, I think, for this chapter. I don't think we're doing molarity until next chapter. Yeah, that next chapter, solutions. So we get something like percent H2O, and we use this, or in the lab we did, or we're going to use it in a lab we're going to do. I can't remember if we did the water of hydration lab or not. Okay? Ask me if you have any questions. When you have a chance, you can email me. But that's how to calculate water of hydrations. All right? So that's kind of concepts. What I want to go to now is, I talked before about solutions, and I said that solutions like salt and water are homogeneous. Well, all solutions are a type of mixture. When I mix things together, it's a mixture. But you can have different kinds of mixtures. So I have a mixture. And that can be just a mixture, or it can be something called a suspension, or it can be a solution. And the difference is suspensions in the middle. Mixtures, let's do mixtures first, are heterogeneous. Heterogeneous. What that means is that they are it's easy to separate the parts. Like if I have red and blue marbles in a bag, that's a mixture. I can physically separate the marbles. The individual particles are large enough to physically separate, and they're not the same. Like I could put all the blue marbles here, all the red marbles here, and if I mix them together and then I cut it in half, it's very likely that one of the halves will not have the same number of blue balls as the other one, or red balls. They're not going to be necessarily the same. That's a heterogeneous mixture. A suspension is a mixture in which the particles will eventually settle out. So when I mix a suspension, for a brief period, it's mostly homogeneous. But it's still a mixture. It can be unmixed. Over time, it will settle. And an example there is muddy water. And if the particles are greater than 100 nanometers, it's a suspension. All right? If the particles are so big that you can physically separate them easily, we don't even call it a suspension anymore. It's just a mixture. It's a heterogeneous mixture. Suspensions are mixtures that can be unmixed, like muddy water. Okay. Now there's another type of suspension called a colloidal suspension. And these are where the particles are from 1 to 100 nanometers. Now a suspension, think of like Italian salad dressing. That's a suspension. I shake it when I want to use it, but if I let it sit for a minute, it's no longer mixed. That's a typical suspension. A colloidal suspension, when you mix it, it stays mixed for quite a while. And it's very dispersed at first, and we call that dispersed phase the colloidal particles, and the medium is the non-colloidal material. So the colloidal material is what goes in, and the non-colloidal material is like the solvent. The colloidal particle is the solute. And the easy examples of this are paint. When you get paint, if you let it sit for a while, the colloidal particles will separate, but then I can shake it, and it's going to stay pretty well mixed for a good day or two without any more shaking. But what determines the type of mixture is the size of the particle. These are going to be, let's just say, greater than 1,000 nanometers in general. Greater than 100 nanometers, it's a suspension, which includes those, I suppose. A colloidal suspension is 1 to 100 nanometers. And if it is less than 1 nanometer, it then becomes, more about colloidals. These are usually cloudy. You can dilute them until they eventually clear out. But the particles are too small to filter. You can filter these, you can't filter these. And they don't settle completely, but they will separate somewhat, like with paint. Other properties of colloidal particles that you need to know. Tyndall effect. And we're gonna have a lab where I'm gonna demonstrate this, but if you take like a laser beam and shine it through diluted milk, you'll notice how the whole milk will start to glow. And that's because the light is kind of being scattered in all directions. It doesn't pass through. It makes the whole solution bright. And your blood is kind of a colloidal suspension. So when you shine a light through your hand and it kind of glows, that's the Tyndall effect. Brownian movement. The particles within a colloidal solution will move randomly, and that's Brownian movement. And a special type of colloidal suspension is called an emulsion. An emulsion is a liquid in liquid, two liquids mixed together. Now, not every liquid in liquid will mix. In order to make them mix, we add an emulsifying agent. An emulsifying agent is something that stabilizes the emulsion. For example, if I take eggs and mix them together, you'll see that that it doesn't mix very well. The yolk and the white and yellow doesn't mix well. Right? But you can add oil. If you add oil to egg, it will mix really well. And you'll form usually this white, thick solution. And that's basically how mayonnaise is formed. So so you add something to it, usually with fat or something, that acts as an emulsifying agent to form an emulsion, which is a liquid in liquid colloidal dispersion. So you have colloidal suspensions, a special type. If it's liquid, In liquid, we call that an emulsion. And if we need something to help it happen, we call that an emulsifying agent. Okay. Now, what we're going to say for the next chapter is this solution part. And what a solution is when the particles are so small that it becomes heterogeneous or homogeneous. So these are homogeneous, meaning that they are the same throughout. So these are homogeneous. And technically these are all, everything over here is heterogeneous. Heterogeneous, homogeneous. Homogeneous meaning the same throughout. If I took 2 cups of Kool-Aid out of the same pitcher, they're going to basically be the same unless I added so much sugar that it's crunchy at the bottom. So let's summarize this, and then I'm going to do a 4-minute video just on the math that I'm talking about down here. Water covers 75% of the Earth's surface. Less than 2% of it is drinkable. Your body is around 66% water. Water is very polar. Because of that, it forms very special hydrogen bonds because of an exposed proton. Water is a solvent to form aqueous solutions. Solutions are homogeneous and usually have small particles. Water has a very large heat capacity, which means it can absorb it takes a lot of energy to change its temperature. Water has a very high surface tension, which is why it tends to form spherical particles. Just a little bonus here, it has a neutral pH, so pure water is neutral, and we're going to get to that. That'll become important when we get to acids and bases. And water is nature's solvent. And I'm gonna stop there, and I'm gonna come back and do the added math review as a separate video. If you're not in honors chemistry, you don't need to watch the next video.